Huh. Hello all. We will wait till 6:05 and then we will start this class. Okay. Huh. Finally. Hello all. I hope I am audible to all of you. So welcome to week 9 of this live session. I am Manoj Shikhar. I am a PMRF scholar at IIT Delhi and I work in the Department of Applied Mechanics, IIT Delhi. I have done my BTech and MTech from IIT Kharagpur and we will be covering problems related to topics discussed in week 9 of the video lectures of solid mechanics. Okay, so in these video lectures, sir has mainly covered the bending of beams. So I will be solving a few problems related to the bending of beams. Now, before starting this, I'd like to declare one thing that we are not allowed to help you with assignments which are active right now on SWAYAM portal. Okay, so please refrain from asking any questions from assignments which are currently active right now. Apart from that, I will be taking some subjective problems here, and I will be showing you the way to solve those problems. And if you have any doubt, you can ask by writing in the chat or unmuting yourself, or you can post your doubts on the discussion forum of SWAYAM portal. So just let me check if it is recording or not. Okay, so it's recording. Maybe we should recapitulate first, possibly a few concepts that will help. So in lecture 23, pure bending of rectangular beams was discussed. And in this, we assume that we are applying bending moments at the end of the beam. Okay, and the beam is not subjected to any other loading. So in general, beam can be subjected to transverse loading, axial loading, or moments at different places, or you can see that there is different distributed force here. So all these are different kind of loadings to which beam can be subjected. So in this lecture, the case in which only the moments about z-axis was applied was considered. Then later on in the lecture, the concept of neutral line, neutral plane, neutral axis was discussed. So neutral line is the line whose length that doesn't change when the beam bends. So initially the length of this curve will be L and capital L, and finally also the length of this curve will be L. So initially this curve would be straight because we're starting from a straight beam. Okay, so I hope you are able to visualize that. And if you like view in 3D, then you will realize that this line is actually a plane. So neutral plane consists of all the neutral lines possible for this beam. And when you look at from this cross-sectional view, if you go and look at this view, look in this view, this line which is formed by different point of intersection of neutral lines with this cross section is called neutral axis. Then we moved on to find like what are the expression of epsilon xx, like in this case it was minus y by r. Then what will be the distribution of shear stress or shear strain. So from this we can see that shear strain is minus y by r, so it will be linear in y, and that is what has been shown here. And you can see that when you increase the y, like if you put y as 2, suppose, so you will get minus 2 by r. If you put y equal to minus 2, then you will get 2 by r. So that is what has been shown here. So in solid mechanics, our convention is any stress or strain with negative sign means compression, or any stress or strain with positive sign means extension. Now, how do we find sigma xx? So we know that in this particular scenario, in this particular loading condition, that our lateral edges, lateral faces, they are traction free. So we can use for isotropic material, we can use this formula, the generalized Hooke's law, and there we will just do sigma y equal to 0 and sigma zz equal to 0, and we will be able to find the relation between sigma xx and epsilon xx. And on working out, we found out that sigma xx is minus E y by r. Now till now, we don't know what is the actual location of neutral axis. So to find that, what we did, since there is no axial force in the body, in this case, so we integrated sigma xx over the area and we found out axial force in x direction. That is the force in x direction. And we equated it to 0. So from there, here should be a y dA. So from there, we found out that integral of y dA over the area is 0. Okay. This means that if you remember from your class 11, this is the formula for centroid. So centroid into area will be 0. So this is the formula for, suppose if I divide this integral of y dA by integral of dA, I get the centroid. So this essentially gives me y bar c, that is the centroid, into A. And in this case, when the beam is a rectangular beam, when the cross section of beam is a rectangular beam or circular beam or any other beam, so in that case, the centroid will be any symmetric beam, not any other beam, any symmetric beam, then in that case, the centroid will be at 0. So that is what we have gotten here. Then we moved on to like find the total moment due to the traction. And the traction here is sigma xx, tau yx, and tau zx. And this was the r vector, like on the cross section. So on cross section, you will be having some point yz. So that will be written as yj hat plus zk hat. And this is the sigma. Now, if I want to know like what is the, because we are applying moment in the z direction only. So we'd like to know what is the component of this moment about O. So if you see, we are applying the moment only about z axis, right? So if we want to know what is the moment about z axis, and we know the total expression, like the expression for total moment, which is this one, what should we do? We should take a dot product with k hat. If I take a dot product of k hat with this expression, I will get the expression for moment in z direction. And after substituting all the values and carrying out the mathematics, we came to this formula that mz equal to minus double integral of y sigma x dA. Okay. And we can substitute the sigma x value by using the formula we calculated here. And then we get mz equal to EIZZ by mz. Sorry, mz equal to EIZZ into 1 by r. So r is the radius of curvature, and so we can the quantity, like we can also replace this 1 by r by quantity called bending curvature, and it is denoted by kappa. So the bending moment mz is defined by bending modulus EIZZ into kappa. Okay. So this is one of the most used formula in solid mechanics questions when you solve for gate. Like if you solve the questions which came in gate, you will encounter this formula a lot. So other variation will be this. They will give you the radius of curvature. Give me 1 second. Sorry for the disturb. Then how do we calculate IZZ? So we know that y square dA is the formula. Now the area, what is the area here? dA. What is dA here? So we are looking at the cross section of this. This cross section is formed by y and z axis. So maybe I should draw it. So the cross section is like this. and I need to find IZZ. So the formula is now what will be the limit of y? So suppose this is 0 and the total height is h. So the height, so the coordinate here will be minus h by 2. And here it is plus h by 2. Similarly, z will vary from minus b by 2 to b by 2. So this is pretty straightforward. In this formula, you have to just substitute the limits. For example, in this case, maybe I should first write dz. So the limit for z will be minus b by 2 to b by 2. Limit for y will be minus h by 2, h by 2. Now y and z are independent of each other. So we can write it like this. So what will be the expression? So from here we will get b. So b times integral of so b by 3 y cube minus h by 2 to h by 2. I should write 3 here for this step. So we will get b by 3 into h cube by 8 minus h cube by 8. So this is bh cube by 12. Suppose if this is a square, then in that case b equal to h for a square. So you will have izz equal to b times b cube by 12. Now you must have read how to calculate these like IZZ, IYY in your first year mechanics course. There we go in detail like parallel axis theorem, perpendicular axis theorem. So I hope you know how to calculate these. Anyways, after that we moved on to see like how the shape deformation will happen due to bending, and we came to know that the beam will bend in z direction also and x direction also. Then we moved on to non-uniform bending. Here, transverse loading was also applied apart from the MZ loading. And then accordingly, we calculated various things, like various quantities. We also got one very important formula, dm by dx plus vx equal to 0, where vx is the shear force in the y direction. So x is like the location at which we are calculating this force. So people get confused here a lot. They think that Vx is like some force in x direction, but no, Vx is a force in transverse direction, and it is at location x. So for example, if I cut here and if the location is x minus delta x, so I write Vx minus delta x, something like that. Okay. So keep this in mind. Then we found out the expression for shear stress tau xy, and the formula came out to be Vx into Qy by Izz B1. All these have been done for the symmetric cross sections now, till now. So let's move on to the questions, and then using questions, I'll try to like make you understand few concepts. The question is like think of a composite beam. Think of a composite beam having rectangular cross section such that one half of the cross section is aluminum They have also told that it has a square shape, means h and the height and breadth are same. Is aluminum while the other half is steel. When such a beam is bent, where will the neutral axis lie in the cross section? Calculate from the bottom line of the cross section. So what they have essentially done, they have given you two different kind of materials. So they have told that. So till now, what we have read only for beams which are made up of one material. So the term composite beam means we are using multiple materials for our beam. So composite is here like how one material is steel, other is aluminium. Okay. Suppose if I had some other material like brass was here, then that will also be called as composite beam, but we are increasing the number of layers there. So think of a composite beam having rectangular cross section. So the beam is actually the combination of these two, right? So this is the complete cross section, and they're telling that one half of the cross section, like this part, is made up of aluminium, and the bottom part is made up of steel. They're telling that we are bending this beam, and they want to know where will the neutral axis will lie. And they have given you the dimensions like total height is 2h, and they have given you E aluminum and E steel, and they've also told that what is like E aluminum is less than E steel. So let's proceed in this question. If you have any doubt while I explain, you can unmute yourself, you can ask, you can write in the chat, you can post on the SWAYAM portal discussion forum. This is aluminum. This is steel. This height is h. This is h. This is also h. And this is h. They're telling you to find where will it exist. The neutral axis exist from this point. Okay, so this is the point of reference. Now, how do we proceed with this problem? So first of all, while looking at this problem, you should realize that though the cross section is symmetric, okay, but we cannot directly say that the neutral axis will lie at the center of this cross section. Okay. And why cannot we say that? Because we have here we have a beam which is made up of more than one material. So if it was completely steel or completely aluminum, the neutral axis would have passed through the centroid. But now it will not happen. So what should be the steps we should take? So if you remember it from the class, what we did there, we did total axial force equal to 0. Okay. And from there, we were able to find that, okay, so this will be the value of, so this is the location where our neutral axis will lie. So let us start with assumption that neutral axis will lie somewhere here from the center. Suppose this is our center. Okay, this is the centroid. Okay. So neutral axis will lie somewhere a distance below neutral axis, the centroidal line. So I'll write it. Let's assume the neutral axis lies a distance below the centroidal axis. Or this is also, we can also write the midline of the cross section. Should write it midline of the cross section. Because why we should not say centroidal axis? Because the masses can be different, or the like centroid of area will be here, of course, but sometimes centroid is used for mass also and other things also. So midline of cross section is a better term. There was no harm in using the centroidal axis, but still. Okay. So what? So what do we know about strain? The formula of strain is epsilon xx equal to minus y upon r. Okay. And the formula for stress is sigma xx equal to E times epsilon xx, which is like minus epsilon E epsilon xx, sorry, minus E y upon r. I have unmuted myself after the call. So this is the formula of stress. This is the formula of strain. So what will happen if we calculate stress in steel? So there sigma xx will be what? Minus E steel into y upon r. This will be and one more thing. Suppose this is the neutral axis. So this is the neutral axis. So from here we are actually measuring the y. So what is this length? This length is like the coordinate of this lowest point will be minus HA and this will be A, right? So we should keep in mind that this y is distance from neutral axis. So minus ES y by r when y is in between minus H minus A to A. Okay. And it will be minus EL EAL y upon r when y is from A to H plus A. So this distance is H. So the total distance from neutral axis is H plus A. Okay. So we can see that the stress is actually discontinuous, like it is not continuous. Strain is continuous, like if I draw the stress strain here. So suppose this is our cross section and this is our midline because I'm using this color for central neutral axis, so I should not show it. So this is our neutral axis. Okay. This is our midline. So the strain distribution will be like So strain is continuous and it will be looking something like that at this point where we have neutral axis, it will be 0. So the strain will be something like this, but it will be continuous. It is linear and continuous. You can see it is 0. 0 at neutral axis. Okay. For stress also, stress will be 0 at neutral axis. So this is the 0 point. Suppose this is our stress. So it will be something like this. And then since EAL is less than our ES, so there will be some decrease here. And then it will be like this. So you can see there is some finite jump here. So here there is some finite jump. Finite jump in stress. So strain is continuous. This is epsilon xx. This is sigma xx. So we know what epsilon xx is continuous. Sigma xx has a finite jump at y equal to a or at midline. Midline of anyways. So to obtain what is the value of a, we will use total axial force must vanish in the cross section. And why it should vanish? Because this is a case of pure bending. Okay. Because of pure bending. We are not applying any axial force. So the total axial force must be 0. So this is the AS means area of steel. Sigma XX steel dA plus A aluminium. Sigma XX A means aluminium dA equal to 0. So this summation will be 0 because this is the force in aluminum, axial force in the aluminium part. This is the axial force in the steel part, and the summation should be 0. So the sigma xxs will be replaced by minus E of steel y by r and the area is dy dz. And this is integrated from minus b by 2 to b by 2 minus h by 2 to h by, sorry, the limits will be minus, let's me, the limits for y are minus h minus a to a, and the limits for z are minus b by 2 to b by 2 for steel. For the aluminum part, the z limit will be same because in z direction there is no change in the material. And here it will be a to h plus a minus e aluminum into y by r dy dz equal to 0. So this is what we will get. And since the terms do not depend upon z, so we can remove the z integral because that will give us a constant b. So we will finally get the integral minus h minus a to a. And since es and r are constant, we can remove those also. So basically, r can also be removed with z integral. So we will have simply es times minus h minus a to a. There will be a minus sign y dy minus eal a to h plus a y dy equal to 0. So if we integrate this, we get minus es into a square minus h minus a whole square by 2 minus eal into h plus a whole square minus a square. So we finally get it like this. So from here you will get expand it. So on expanding we will get minus two ah minus a square plus eal upon s equal to 2ah plus h square. Here it should be h square. So from here we will get a equal to h upon 2 into 1 minus eal upon es divided by 1 plus EAL upon ES. So finally, we can write A equal to H by 2 ES minus EAL divided by ES plus EAL. So if you look at this problem, if suppose we have the same material here, if suppose steel, if it was made up of the same material, not aluminum and steel. So I can replace AL by S. So in that case, A will come out to be 0. And that is essentially what we get when we when we solve this in class for a single material. And also one more thing to look at here is like in question, it was given that EAL was smaller than ES. So this quantity is less than 1. Okay, so EAL by ES is less than 1. Hence, A is positive, means that the direction we took was correct. So here the neutral axis is below this midline. Suppose if EAL was greater than ES, then in that case, this quantity would have become negative, and that implied or that meant that the neutral axis is somewhere above. Okay, not here, not below A, not A below midline, but A above midline. Okay, so that is the meaning. So while solving this problems, we should like be attentive about these things because they generally give us the idea, okay, what kind of material is getting used. Okay, if the neutral axis is really below or is it up, that is necessary to understand. So this was question number 1. Question 2 is a composite beam of cross section is subjected to a beam of composite cross section is subjected to bending moment Mz equal to 30 kilonewton. And they have told you to find the curvature induced in the beam, the maximum bending stress in the wood, and the maximum bending stress in steel. So composite cross section means like it has been made using different cross sections. Okay. So you can see the wood is of this cross section. This is the steel has different cross section. So the first step will be to find the uh, to find the bending stiffness of this cross section. Okay, so total bending stiffness. But the first step at the first glance, you should realize that this is a symmetric. This cross section is symmetric. Okay, so if the cross section is symmetric, then its neutral axis will be the mid horizontal line of the cross section. So here the neutral axis will pass through where the mid horizontal line, the midline. So that will be the first observation you should have. The cross section is symmetric. It doesn't matter, it is made up of composite cross section. If it is symmetric overall, the neutral axis will pass through the mid horizontal line in the cross section. Okay, so let's draw it. Let's draw the question, the figure in the question. So they have given you a stick. Okay, question number. It was actually question number 5 in my assignment sheet, so I will write rename. Actually, I should write 1, 2. So they have given you steel. This is steel. Then they have given you wood here. And then here there is steel again. So we know one thing for sure, that the neutral axis will be the mid horizontal line of the cross section. So this is our neutral axis. Why? Because the cross section is symmetric. Symmetrical. With respect to geometry as well as the material distribution also. Okay. In last case also the cross section was symmetric, but the material distribution was not symmetric. At the upper point it was only aluminum, and at the lower point it was only steel. Here the cross section is symmetrical with respect to material also. Okay. So we have to calculate the total step 1, calculate total bending stiffness. Bending stiffness. So what will be EI total? EI total will be EI steel plus EI wood. So here they have given some dimensions also, so I will write those dimensions also. So they have given that this is 120 mm. This is 6 mm. This is also 6 mm. Okay. This length is 60 mm. This length is 60 mm. And this length is 90 mm. Okay. This is your Y direction. This is your Z direction. And the other data is E of wood is 10 GPa. E of steel is 200 GPa. You have to find, they are given that it is subjected to moment mz equal to 30 kilonewton. First is find curvature induced in beam. Second part is maximum bending stress in wood. And the third part is maximum bending stress in steel. So we already know steel's stiffness. We know these like Young's modulus of steel and Young's modulus of wood. So we need to find like what is the I of steel and what is the I of wood. Okay. So I of steel will be what? It is a rectangular cross section. So 1 by 12 BH cube. I is equal to 1 by 12 into B of steel into H of steel cube. Okay. And since we have 2 bars of steel, so we can multiply this by 2. Okay. Here to calculate the total I of wood, you can follow two different methods. One is like you can calculate the I of wood about its centroid, its own centroid, and you can use parallel axis theorem. Or we can consider that we have two cross sections, like the complete this cross section, the inner one, and we are subtracting this part from that. So I will follow the second part, which I am telling. So, so I will assume that I have a complete wood. Okay, and I will subtract from it the inner part. So this is how I will calculate the I of wood. So anyways, so the total height of steel will be what? So from the figure, you can see that H steel equal to 60 plus 90 plus 90. 60 plus 90 plus 60, sorry. So 210 mm. So this is equal to 0.21 meter. What is B steel? This is 0.006 meters. Similarly, the total height of this block is 0.21 meter. The breadth is 0.12 meter. It is given. Here the breadth will be 0.12 meter. And the height is 0.9 meter. So we have to just substitute it here. So I steel is 1 by 12 into 0.006 into 0.21 cube into 2. This 2 is coming because there are two steel strips. Keep in mind 1 and 2. There are two steel strips, right? So that's why I'm multiplying it by 2. IW is what? 1 by 12 into, let's say W1 and W2. Okay. So BW1 into HW1 cube minus 1 by 12 into BW2 into HW2 cube. So I would will be 1 by 12 into 0.12 into 0.21 cube minus 1 by 12 into 0.12 into 0.09. Oh, sorry. It should be 0.09, not 0.9 meter. So now to calculate EI total, you have to just substitute IW and IS there. So EI total will be ES into IS plus EW into IW. So you can do the calculation. Now we have to find like what is the curvature induced in the beam. Okay. So to find the curvature induced in the beam, we can use formula directly. So we can use kappa equal to mz upon EI total. Okay. They have given you the value of mz 30 kilonewton meter. I think it should come with some other unit. Here it should be Newton meter. So here you will write 30 kilonewton meter divided by whatever EI total you have calculated from here. Pi total. And you will get the value of kappa. So this is the kappa induced in the beam. Now they want like what is the value of maximum bending stress induced in steel, in wood. Okay. So maximum bending stress induced in wood. So for this, what you will do? We know that the maximum bending stress will be where either at this point or this point. Okay. Why? Because we know that epsilon is minus y by r. So the maximum will be at the end points. So for wood, sigma wood will top will be equal to EW into kappa at top or bottom. Okay. So what is the point for top? So EW into kappa at 0.45 plus 0.045 plus 0.06 meters. Okay. So the top is where from here, this distance is 0.45 plus 0.6. Similarly, the maximum bending stress induced in steel is sigma S top equal to ES, the Young's modulus of steel into kappa at top or bottom. Okay. So it will be ES into kappa at 0.045 plus 0.06 meters. Okay. Now, this kappa which we have calculated, this is for the neutral axis, right? So to calculate the kappa K 0.04 plus 0.06 is, keep in mind kappa is 1 by r. Kappa is 1 by r. Okay. So from here you can find what is the neutral, like suppose if this is denoted by Kn. So I will find what is the radius at neutral axis. It will be 1 by kappa n. Okay. So kappa at 0.045 plus 0.06 will be 1 by radius at 0.045 plus 0.06. And what will be the radius at that point? It will be 1 by Rn minus 0.045 plus 0.06. So from A, you actually need to do the inverse of whatever you find in A. That will give you the radius at the neutral axis, and you will have to use that Rn to calculate the kappa at this point. Okay. So here the assumption I am taking is that our beam bent like this. Okay. So if this is the so if this is Rn, this will be Rn minus this distance, right? Suppose the distance is L, so Rn minus L. And that is what has been written here. Rn minus 0.045 plus 0.06. I hope I have made myself clear here. Now the next question is a flat steel bar, 1 inch wide by 0.25 inch thick. Okay, so they have given you the cross-sectional details that it is 1 inch wide, B is 1, and the thickness is the total edge is 0.25. And the length is 0.40 inch long, is bent by couples applied at the ends so that midpoint deflection is 1 inch. Compute the stress in the bar and the magnitude of applied couples. Use E equal to 200 GPa. So they have given you what? They have given you a flat. They have given you a flat rod. And the cross section of this rod is this is 1 inch and this is 0.25 inch. Okay. They are telling that they have applied moments here. And after applying moment, what has happened? The rod has deformed. The central point, this has deflected by 1 inch. So so this deflection is 1 inch. Okay. They given us that the total length was 14. So this is 20. And this is 20, right? And we have applied some moment. And because of that moment, this deflection is there. 1 inch deflection is there. We need to compute the total. So compute stress in the bar and moment applied or the magnitude of couple applied. So till now, what we have read in the bending, that when we apply the bending moment, our body bends, right? So if this is rho, this radius is rho, this radius is rho. So this whole length, this will also be rho, right? Suppose if the rho is the radius for the neutral axis. So this is rho. Now, if you go from geometry, suppose I will give names to this point now so that I can easily suppose this point is C and this is D. This is E. So the length of AC will be what? It will be rho minus 1. So we have a right angle triangle here. We have a right angle triangle here. Here, this length is rho. This is rho. This deflection is deltas. And overall, this length was rho, right? Because this corresponds to the same radius as these. So this will be rho minus delta, right? I hope I have made myself clear here that why is it rho minus delta. And we also know this length is L by 2, where L equal to 40 inches, sorry. L equal to 40 inches, this length is L by 2, delta equal to 1 inch. So from here we can find the radius of curvature rho. So how will we find? We know that this angle will be 90 degrees. So rho, using Pythagoras theorem, C square equal to rho minus delta whole square plus L by 2 whole square. Hypotenuse square equal to A square plus B square. So rho square equal to rho square plus delta square minus 2 rho delta plus L square upon 4. And from here we will get rho equal to L square upon 4 delta plus delta into 1 by 2. So if we substitute everything, we will get rho equal to 200.5 inches. Let me calculate it also just to show you. 40 square upon 4 into 1 plus 1. So this is 401.2. Oh, rho is 200.5 inches. So from here, what we can do, we can find moment. M equal to EI upon rho. E has been given. So they have given E equal to in question, it is given in GPA. So if you convert it, you will get the value I have written here. So I will write what they have given in. So E equal to. So this point should be some other point. Let's write it as G. So they have given E equal to 200 GPA. So if you convert it, you will get this value in LB inches square. So 29 into 10 power 6 into I will be 1 by 12 into B is 1, H cube is 0.25. Cube divided by rho we have got 200.5. y. So this comes out to be 188.3 lb inch. Okay. So this is the answer we get. To find the stress, we can replace this by E by rho into y. This is the value of stress in the bar. Okay. So you can replace E by rho here, and with respect to y, stress will vary. So in question number 7, they are given in a laboratory test of a beam loaded by end couples. The longitudinal fibers at layer AB, so this is our layer AB, is found to increase 60 into 10 power minus 3 mm, whereas those at CD decrease 100 into 10 power minus 3 mm. Okay. In the gauge length, the length is 200 mm. Okay. They've given you using E equal to 70 GPa. Determine the flexural stress in the top and bottom fibers. So you have to find what will be the stress at the top fiber and the bottom fiber. Now in this question, one interesting thing is there that we don't know where the neutral axis is because we don't know the cross section. Okay, we don't know the exact cross section of the 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 shape of the cross section is not mentioned in the problem, so we don't know where will be the neutral axis. So we cannot assume that the neutral axis will be at the center. Generally, if the cross section was symmetric, suppose if there was some symmetric cross section here, we would have assumed that here at the center the neutral axis will be there. But we don't know the cross section, so we will have to find the location of we'll have to find the location of the neutral axis. So let's solve this problem also. Question number 7. So they have given us something, some random cross section. And they have given us points. This is A, this is B. The length is 200 mm. Okay. So I think this will be used for calculation of epsilon xx because they have given the increase in length, right? And then we have CD here. They have also given the location of this point B. This is 30 mm from top. And this is point D is 75 mm from bottom. These lengths are required when we want to find the stress at the top or bottom fiber. Okay, so there we will need this length. And this length is 120 mm. This has been given in the question. What they want is, so we will assume that our Neutral axis will lie somewhere x distance from AB. Okay, so this is our AB. So our neutral axis will lie somewhere here, like we did in other question also. We assume that, okay, so here, let us assume that at some x distance, our neutral axis lies. So this is our neutral axis. Okay. So we know that the strain will be continuous. Okay. So epsilon xx is what? Minus y by r. Maybe here I should write something else like eta or something. X. So r equal to what? Minus y by epsilon xx. So y by epsilon xx will be equal to r. Now what will be the value of y? So from if we look from neutral axis, the value of y will be eta for AB, and for CD it will be eta minus 120, right? Because suppose this was eta, this whole length will be 120 minus eta. There is no doubt about it. But what will be the coordinate here? So the coordinate here will be minus 120 minus eta, right? So R will be equal to what? R equal to minus eta upon epsilon xx, that is epsilon AB, equal to minus of, let's write it as minus R. So minus R will be what? Y AB upon epsilon AB equal to Y CD upon epsilon CD. Okay. So what is YAB? YAB is eta. YCD is minus 120 minus eta. Okay. And how do we calculate epsilon EB? So they have given us in the question. In the question, what they have given? They have given that increase in AB equal to 60 into 10 power minus 3 mm. Decrease in CD equal to 100 into 10 power minus 3 mm. And gauge length was, gauge length means the initial length was 200 mm. So from here we can calculate epsilon AB equal to 60 into 10 power minus 3 divided by 200. Okay. So this is 3 upon 10. So 0.3. So I missed this part. So this will be 3 into 10 power minus 4. Epsilon AB is 3 into 10 power minus 4. Epsilon CD is 100 into 10 power minus 3 upon 200. So 5 into 10 power minus 4. With negative sign, of course, because epsilon CD is what? Compressive. So it should come with a negative sign. So substituting here, we will get eta upon 3 into 10 power minus 4 equal to 120 minus eta upon minus 5 into 13. So from here, this will cancel out. This negative sign will cancel out. So 5 eta equal to 120 into 3 minus 3 eta. Implies that 8 eta equal to 120 into 3. So eta equal to 45 mm. Similarly, since this r is the radius of curvature of the neutral axis, so if we look at this r from this point, the point on the top, let us assume we are looking from some point P here. So there also we can use the formula minus r equal to, so there we will use minus r equal to, suppose this P and Q, 2 points are there. So epsilon PQ means the stretch in the top. Okay. I think it should be written here. So let's say we have some point here, PQ. Okay. So for point PQ also we can write minus r equal to y PQ upon epsilon PQ equal to YAB upon epsilon AB. Okay. Now we know that the YAB is eta, and what will be YPQ? YPQ will be, implies that eta plus 30 upon epsilon PQ equal to eta upon 3 into 10 power minus 4. We know the value of eta is 45. So implies that 75 upon 45 into 3 into 10 power minus 4 equal to epsilon PQ. So this is also equal to epsilon top. Okay. So 15.5. So epsilon PQ equal to 5 into 10 power minus 4. Now we have the like this is equal to epsilon top. So the sigma top will be what? Epsilon top into E. So they've given E equal to 10 power 17 to 10 power 9. And we have calculated epsilon as this is 35 MPa. Okay. Similarly, to calculate the stress in bottom, we can do this. Suppose we have some points TU here. So we can write minus R equal to YTU upon epsilon TU equal to YAB upon epsilon AB. Okay. Then YTU is what? YTU will be this length. This length is YTU. So this is 120 minus eta. This length is what? This is 120 minus eta. So 120 minus eta plus 75. So YTU will come with a sign because we are going in the negative direction, right? So YTU will be minus of 120 minus eta plus 75. So this is the total length. Epsilon TU equal to eta upon epsilon AB. So from here we can calculate epsilon TU equal to minus 120 plus minus 45 plus 75 divided by 45 into 3 into 10 power minus 4. So epsilon TU is minus 6. 120 plus 30, 150 upon 15 into 10 power minus 4. So this is minus 10 into 10 power minus 4. So to calculate stress, this is also equal to epsilon bottom. Okay. So sigma bottom will be E into epsilon bottom. So 70 into 10 power 9 into minus 10 into 10 power minus 4. This comes out to be 70 MPa with negative sign. So this is a compressive stress. So the bottom point will have compressive stress. So let's have a break for 5 minutes, and then after that, we will restart the session. Hello all, welcome back. So let's move on to the next question. I think this will be the last question I will take today. So the question is, a laminated beam is composed of 5 planks, each 6 inch by 2 inch. So the width of the beam is 6 inch and the height is 2 inch. The width of the plank is 6 inch and the height of the plank is 2 inch. And we have stacked 5 different planks here. So the total height of beam becomes 10 mm, 10 inches, right? It is written that they are glued together to form a section 6 inch wide by 10 inch height. That is what I told. The allowable shear stress in the glue is 90 psi. So they have given you the allowable shear stress equal to 90 psi in the glue. So between these two surfaces, maximum shear stress could reach is 90 psi. And the allowable shear stress in wood is 120 psi. So in between wood, so this is the, suppose this is one plank. So the shear stress of this one plank would be like the maximum shear stress which each of the planks can withstand is 120 psi. And it is also given the allowable flexural stress in the wood is 120 psi. So when beam has been composed as a whole, in that case, when suppose we are bending it, so the flexural stress which it can withstand is 120 psi. Now they are telling that determine the maximum uniformly distributed load. So we have to apply a UDL, uniformly distributed load, that can be carried by a simply supported beam on a 6 feet simple span. Okay. So, so let's solve this problem then. So they have told that we have a simply supported beam. Question 1. This is our beam. Okay. And it is simply supported. Each of these has a height of 2 inches. So the total height is what? Total height is 10 inches. We are applying one UDL. So to proceed, what we will do, we will cut a section here. Okay. Before that, let us assume the distribution is W. And because this is a symmetric thing, so we can so for this case, we can find the reactions and the reactions will come out to be WL by 2 and WL by 2 at the each of the ends. Okay. That's the last point is. So this is WL by 2 here and WL by 2 here. This is loaded here. We can find these reactions from your first year mechanics concepts, okay? So because the time is very less, I will have to pace it up. Now, after cutting this cross section, we will have something like this. And this is our x-axis. This is our y-axis. And z-axis will come out like this. Our cross section is something like this. This is y. This is z. This is 6 mm, 6 inches. And this is 10 inches. So if we take the right part, so we have WL by 2 here. We have Vx on this face. We'll have moment on this face, mzx. And we will have the distributed load here. And this length is what? L minus x. Okay. So if we do summation of force in y direction and we equate it to be 0. So we have minus Vx minus W into L minus x plus W into L by 2 equal to 0. So from here we will get Vx equal to minus W into L by 2 minus x. Okay. And suppose if we calculate the moment about this point, so this point is O. So summation of moment about O will be equal to 0. And we are assuming that counterclockwise is positive. Okay. So first of all, our mx will come. So it is minus mx. The moment due to Vx will be 0 because it is passing through the same point. The moment because of WL2 will be plus WL by 2 into L minus x. Okay. And the moment due to this distributed load will be minus W into L minus x whole square by. This will be equal to 0. So from here, our mzx will be equal to W. This is quite weird. L by 2. W by 2 L minus x. We should take the W L minus x by 2 common, and here it will be L minus 6. So Wx into L minus x on. Okay. Now, one thing to note is that rectangular cross section. Our cross section is rectangular in this problem, right? So rectangular cross section is symmetrical about y and z axis. Symmetrical about y and z axis. Hence, Y and Z axis are also the principal axis. So also in our problem, we have applied the load. So in this problem, we have applied the load along Y axis, which happened to be one of the principal axis. That is one of the principal axis. Okay. Thus, as a result, we will have in plane bending. In plane bending. Now the UDL we have applied, it will lead to both bending moment and shear force at a cross section, which we have already seen. We have already found it. The expression of Vx and M. Okay. Cross section leading to non-uniform bending. So this is not a case of pure bending. This is what I want to say basically. Okay. Thus, to find the maximum flexural and shear stress, we need to find the bending and shear distribution. Bending and shear stress distribution. Okay. Now, due to symmetrical bending, so you see the bending is symmetrical. It is non-uniform, but it's symmetrical. Okay. The formula for bending and shear stress will be we have already done this thing in class. What are the formulas? So sigma xx is simply mzx y upon izz and tau yx is vx upon vx into qy upon izz into b. Actually, I think I have written done some mistake here. It should be my by Iz. So these are the formula we need to use to calculate the sigma xx. Now the question asked what? They asked determine the maximum uniformly distributed load that can be carried by simply supported beam on 6 feet span. Okay. So they have given you the length L equal to 6 feet. The length of the beam is 6 feet. And they're asking that what will be the maximum UDL, the value of maximum UDL. Okay. So what we have to do, we have to find the maximum values of each of the bending stress. So also we know the expressions. Okay, so we know the expressions of our bending. Let me write those expressions here also. So from these, we can find the maximum values of Vx and Mx. Like there are different methods. One method is you can like draw the BMD and SFD, and you can from there see that at which point this will be maximum. Other thing could be you can use calculus. So you can do dVx upon dx. This will be sorry. So to find the maximum, value of sigma x, we need to know that what is the maximum value of mzx, right? And accordingly, we can substitute y and izz. So the maximum value of mzx can be calculated as dmz dx equal to, if we set the differentiation of mz with respect to x equal to 0, we will get that where the mz will have a maxima or minima. And on double differentiation, we can say that, okay, if it is a maxima or minima. From BMD, you can directly see that the maximum of the bending moment will be at the center. But for the sake of this class, I want to calculate it here. So this will be W into L minus X upon 2 plus Wx by 2 into minus 1 equal to 0. So from here, it is W, this 2 and W can be removed from here. So we will have L minus x equal to 0. So from here we get x equal to L by 2. Now, if this is a maxima or minima, for that we need to differentiate once again. So del 2 mx del x square is so since W is positive, del 2 mx by del x square is negative, less than 0. Hence the point is maxima. Hence mz at x equal to L by 2 is a maximum. So maximum bending stress. sigma xx would equal to, we need to put two coordinates, right? X and y. So mz x y upon izz, max of x zx upon izz to max of y y. So maximum of moment will be where? At L by 2, right? So from here we can calculate it also. So at x equal to L by 2, we have to calculate the moment, and y will be maximum at y equal to h by 2. So here it will be h by 2 and here it will be izz. So what is m L by 2? This is w by 2 into L by 2 into L minus L by 2. So w L cube by 8. W L square by 8. Sorry. So our sigma xx max for wood will be WL square upon 8 into h by 2 divided by 1 by 12 into b h cube. Remember here h equal to 10 inches. Okay. Remember this, the total height of the beam. So from here we will have 3w L square by 4bh square. And this should be less than sigma xx tolerance of wood, whatever they have given. I think this was 1200 psi. Okay, so it should be less than this. Now we need to find the maximum shear stress. So for maximum shear stress, we have to evaluate for both glue and wood. Okay, in both we have to see and then we have to compare accordingly. So tau y max. We know the formula of tau y x max, right? So this is maximum of x comma y. Vx qy izz, and since b is constant here, so it will be b, not. So this is what izz and b are constant, so I will remove them. Max of x vx and max of y qy. Now what is the expression of qy? So qy is the first moment of area of shaded area. First moment of area of shaded area, right? So this is equivalent to area of the shaded region into the centroid of the shaded area, centroid of the shaded area. So suppose that I already done this in class, then also I will write it. So suppose this was the neutral axis, and we know that this is h by 2, and we are looking somewhere here. So this is our shaded area, okay? So what will be the area of shaded area? This is B. So B times h by 2 minus y will be this length. And the centroid will be where? At y plus h by 2 minus y by 2. So this will be the centroid. So the final form will be b by 2 into h square upon 4 minus y square. So this is Q. And maximum of Qy will be when y equal to 0. So will be at y equal to 0. So max of y equal to 0 Qy is b h square upon 8. So therefore for wood, tau yx for wood, max for wood will be v at x equal to L, Q at 0 by izz into b. Now why v at x equal to L? Because v was a monotonic function. So you can see v was a monotonic function. So at x equal to L, it will be, what will be v at x equal to L? It will be WL by 2. So this is WL by 2 into BH square upon 8 divided by 1 by 12 BH cube into B. So this comes out to be 3WL upon 4BH. And it should be less than equal to tau XY tolerance of wood. And this is given in the question that what is the value. For wood, it is 120 psi. So this is less than equal to 120 psi. Now we have to find the shear stress between the glue. Okay, so what will be the shear stress in glue? So tau yx max glue. Now for this, we have to keep in mind that glue is not present everywhere. Okay, glue is present only where we have our planks connected with each other. So these are the points where glue will be present. So while calculating the Q max, the first moment of area. So while calculating the Q max, this Q max for glue, we cannot put y equal to 0. There we will have to put a different value. So suppose this is our neutral axis. Okay, so this is our neutral axis. These blocks are of height h by 5. Okay, the total height is h. Total height is h. So the nearest y is at h by 10, right? So tau y x glue max for glue will be max of x comma y Vx Qy upon Izz into B. So here max of y Qy will be will be at y equal to h by 10. Okay. So max of y equal to h by 10. Qy is what? H b by 2 into h square by 4 minus h square by 100. So this will be so Qy max will be 3 by 25 bh square. We already know V is that x equal to L, and we know this is VL by 2 equal to, sorry, VL equal to WL by 2. We already know this. So we will substitute it here and we will get the tau y max. WL by 2 into 3 upon 25 BH square upon 1 by 12 BH cube into B. So this will come out to be 18 WL upon 25 BH. It should be less than tau XY tolerance of glue. Okay, and this is what this value is given as 90 psi. So this is 90 psi. So from these expressions, so from expression 1, this is expression 2 and 3. So from 1, 2, and 3, we shall get different values of W. Okay, different values of W. And the maximum allowed W would be minimum of whatever we get. Okay, so suppose if from here, maybe I should write it as so from here if we get W3, okay, if from here I get W2 and from here I'm getting W1, then minimum of that will be the value of UDL. Okay, so minimum of that would be the value of UDL. So I hope this question is clear to all of you. If any one of you has any doubt, you can unmute yourself and ask. You can write in the chat. Otherwise, it's already 8:10, so I will end the class otherwise. Anyone has any doubt, you can unmute yourself and speak. Okay, so since none of you has any doubt, I will end the class here. I will meet you all again next week on Tuesday from 6 to 8 p.m. And you can also watch these videos. We actually upload these videos on YouTube also. You can get the access through SWAYAM portal, or you can directly search for like live sessions of solid mechanics by Manoj Shikhar, and you will be able to find these videos. So this was week 9, and let's meet again next week. Thank you for joining. Have a great day ahead. Bye all of you.